Hey everyone, in this video I'd like to review the delta-epsilon definition of a limit. So what I'm going to do is draw a picture and talk about what the definition says geometrically, and then we'll write out the formal definition and all of its rigor in words. So let's start with a picture here of a graph. I'll make the axes in magenta because that's what color I have, so we'll just go with it, right? Now the curve here is I'm gonna put a hole around here, and we'll say that this is our function y equals f of x, and we want to try to compute the limit as x approaches the value where this hole is here. So let's say this is our point A. So this is the point that we want to compute the limit of the function. So we want to know let me write it down. We want to know the limit as x approaches A of this function f of x. And just by looking at this picture here, we can see that if the limit exists, it should be right about at this height, right? So let's call this height L. And what the delta epsilon, the formal definition of a limit, says is if we choose a value, a small number generally, but it can be any number, that we'll call epsilon. So I'm going to say this distance here is epsilon. And then we draw a horizontal strip here, and then we take the same exact amount, the same exact epsilon, and we draw a strip below. All right, so now the value at this height is L plus epsilon. The value at this height is L minus epsilon. Then the question is, how far can we vary from this point A down below and be sure? So how far away can we go from this point A on the x-axis and be sure that up above that our curve is within this epsilon strip? It's really 2 epsilon, right? Epsilon above and epsilon below. And you can see that there are different answers, right? So our curve crosses over and exits our epsilon strip in 2 points. On this side, which by the way, that doesn't always happen, but in this case it does happen. So on this side, we have this x value down here, right? So we can only go that far. On this side, we can go all the way out to this far. And I'm going to label these two distances here delta 1. So that's the distance that we can travel to the left from A. And then the distance to the right here, I'll call this delta 2. And we want to make sure, we want to be able to say something about this A, how far we can get from A, and ensure that we're always going to remain in the strip. Well, if we choose our delta 2 to be our delta, then what we're really saying is that we can go this far away in both directions. But if we copied that delta 2 over to here, right, it would say that we could go somewhere like maybe way out to here. But look at, we've left the strip at this point. So what you have to do then is you have to restrict yourself to the smaller of these two values. So we have to restrict ourselves to stay between, this strip right here, so this delta strip in the x direction. And so we just copy our delta 1, and we have to stay here. And now within this strip, we can be sure that in both directions that we are within our epsilon strip up above in the vertical direction, right? So if we stay within this delta 1 in the horizontal direction, we will remain, our curve will remain between the epsilon strip, right, in the vertical direction. So this right here then, what we'll say is we'll put our delta, in this case, as a function of this epsilon, equal to delta 1. Why do I say it's a function of epsilon? Well, if we make epsilon smaller, we're going to have to change the delta, right? So if the epsilon gets smaller, the delta presumably will have to get smaller as well to make sure that we stay within the strip. So delta always depends on the choice of epsilon. Okay, so let's write this out now in all of its formal glory. It says the following. So here's our, again, delta epsilon definition of a limit. So let's let f be a function defined, so defined on an interval containing the point A. So it needs to be defined near A, that's what we're saying here. So containing x equals A, but not necessarily defined at A. So in this picture I drew a hole there. We never actually get to A though, right? So we have to say this then. So not necessarily at this point x equals A. All right. Then we say that the limit of this function f as x approaches a is L. So this is what we're defining, right? The limit of f as x approaches a, all right, is L. If and only if. And now we need to write out the technical details of the picture that we just drew, right? So if and only if, for every epsilon greater than 0. So this is the choice of our epsilon strip. Epsilon, by the way, looks like an E, right? This is a Greek letter epsilon. It looks kind of like an E, and it represents some kind of error or tolerance that you're acceptable, that you deem to be acceptable up above. And of course, you're going to probably want to choose it to be very small in general, right? But if and only if for every epsilon greater than 0, there exists a delta. So I'll call this a number delta. And delta depends on this epsilon. So I'm going to write it like that. Delta equals delta of epsilon. Depends on the choice of epsilon. Such that. So now we need to say properties of the delta and the epsilon, right? So such that whenever, what's going to be true? Our x value has to be within delta of a. So how can we write that? Well, we can use absolute value to measure this distance here. So the distance between a and any point here, so we want our point to be x minus a has to be within delta, but we don't want to actually get to the point, right? So we're going to say it like this. So whenever x minus a is greater than 0 but less than delta, all right, then we can be sure. So in this case, we can be sure that what's true up above, that our function value is within the epsilon strip, right? So our function value is within the epsilon strip. And so that's what we say down here. So then the conclusion is then f of x, for this x value that's within our delta strip, minus L, so minus the limit, has to be less than epsilon. And this is true for any choice of epsilon, right? So for every choice of epsilon. That right there is the limit definition, the delta epsilon definition of a limit. So this is the formal technical definition. It's pretty wordy, right? It's got a lot of symbols. Some of the symbols are Greek. So it's hard to just read that and understand exactly what it means to be a limit. But when you look at the picture, it kind of helps you out, right? So it tells you, again, you want to be sure that your function values are within the red strip. And the question is, what do you have to choose for the boundaries down below in the x direction to be sure, right, that your function will always remain between the red strip? So what kind of strip do you have to bound your x values by? That's the question. All right, and then we'll finish this off by saying, of course, in this case, we write that L is equal to the limit. This is just our notation for limit, right? The limit as x approaches a of f of x. All right, and so that is the formal delta epsilon definition of a limit. It's the only definition. We know how to compute them. We've made heuristic arguments about, what does it mean to be a limit. We've drawn a lot of pictures, right? But this is the formal definition, so you need to know this.